Have you ever wondered how electric currents create magnetic fields? Or how do magnets work to help us navigate? Let's dive into the fascinating world of magnetic effects of electric current. Before we begin, a magnet is a material that generates a magnetic field, enabling it to attract or repel other materials with magnetic properties. For example, lodestone, a natural magnet, can attract materials such as iron, nickel, and cobalt. Every magnet possesses two poles, north and south, which are inseparable. Magnetic poles exhibit the properties of attraction and repulsion. Like poles repel each other, while opposite poles attract. An electric current carrying wire behaves like a magnet. Electromagnets and electric motors involve the magnetic effect of electric current, and electric generators involve the electric effect of moving magnets. Compass needles get deflected on passing an electric current through a metallic conductor. A bar magnet is a solid, typically rectangular object made of materials like iron, steel, or other ferromagnetic substances with natural magnetic properties. When suspended, its north pole always points toward the Earth's north pole. This characteristic makes it crucial for navigation. Properties of magnet. Every magnet has two poles, i.e., north and south. Like poles repel each other, unlike poles attract each other. A freely suspended bar magnet aligns itself in nearly north-south direction, with its north pole towards north direction. Magnetic field and field lines. A magnetic field has both size and direction, and its orientation is determined by the movement of a compass needle's north pole within the field. By convention, magnetic field lines flow outward from the north pole and inward toward the south pole of a magnet. The intensity of the magnetic field is depicted by the proximity of the field lines. A denser concentration of lines indicates a stronger field, resulting in greater force on the pole of another magnet placed in that area. It is observed that field lines do not intersect. If they did, it would suggest that at the point of intersection, the compass needle would indicate two directions, which is impossible. H.C. Oersted was the first person to state that electric current has a magnetic field. Imagine the force you feel when you bring two magnets close to each other. This force spreads out around the magnet and influences nearby objects. When we mention a magnetic field, we are referring to this invisible area around a magnet where its power can be sensed. Magnetic field due to a current carrying conductor. Magnetic field due to currents through a straight conductor. Concentric circles can represent it at every point on the conductor. Direction can be given by right-hand thumb rule or compass. Circles are closer to the conductor. If you increase the current, the needle's deflection increases as well, showing that the magnetic field strength at that point rises with the current. Magnetic field is directly proportional to strength of current. This change happens because the magnetic field weakens as you move farther from the wire. Magnetic field is inversely proportional to distance from conductor. Right hand thumb rule. If a current carrying conductor is imagined to be held in the right hand such that the thumb points in the direction of the current, then the tips of the fingers encircling the conductor will give the direction of the magnetic lines of force. Where I denotes the direction of current, B denotes direction of magnetic field lines. Magnetic field due to current through a circular loop. The magnetic field around a circular loop forms concentric circles that expand outward. Near the center, these circles appear as straight lines due to the contribution of each wire segment in the same direction, confirmed by the right-hand rule. The magnetic field strength increases with the current in the wire and is further amplified if the loop has multiple turns, as the fields from each turn add up. As we can see the illustration below. Factors affecting field lines. Magnetic field is directly proportional to the current passing through the conductor. Magnetic field is inversely proportional to the distance from the conductor. Magnetic field directly proportional to the number of turns in the coil. magnetic field due to a current in a solenoid. A solenoid is a cylindrical coil of tightly wrapped insulated copper loops, where one end acts as a magnetic north pole and the other as a south pole. Inside the solenoid, straight and parallel magnetic field lines create a uniform and strong field capable of magnetizing materials like soft iron to form an electromagnet. TIP. When we look at any end of the coil carrying current, if the current is in anti-clockwise direction, then that end of coil behaves like north pole. And if the current is in clockwise direction, then that end of the coil behaves like south pole. Force on a current carrying conductor in a magnetic field. French scientist André Marie Ampère proposed that a magnet exerts a force on a current carrying conductor, demonstrated by the movement of a current carrying aluminum rod in a magnetic field. The force's direction depends on both the current's direction and the magnetic field's orientation. The force is strongest when the current is perpendicular to the magnetic field, and its direction can be determined using a simple rule. The diagram demonstrates the force on a current carrying conductor in a magnetic field. The aluminum rod AB is placed between the poles of a horseshoe magnet, and a current flows through it via a closed circuit with a key B. The rod experiences a force, blue arrow, perpendicular to both the current's direction and the magnetic field, causing it to move, illustrating the motor effect. Fleming's left-hand rule. The left-hand rule states that if the thumb, forefinger and middle finger of your left hand are stretched perpendicular to each other, the forefinger shows the magnetic field's direction, the middle finger the current's direction, and the thumb the force's direction. The human heart and brain produce significant magnetic fields, utilized in medical imaging techniques like MRI to visualize internal organs. A galvanometer is a device that detects the presence and direction of current in a circuit. There are three wires: the live wire, red, positive; the neutral wire, black, negative; and the earth wire, green, for safety. In India, the potential difference between the live and neutral wires is 220 V. The earth wire prevents electric shocks by providing a low resistance path for current leakage. Especially in appliances with metallic bodies, a short circuit occurs when the live and neutral wires accidentally touch, causing low resistance and potential overloading. Overloading happens when a conductor carries more current than its capacity, leading to overheating and possible hazards. Electricity flows from the pole to the main supply through a fuse for safety, and then to the electricity meter to measure usage. The distribution box directs current to separate circuits using live, red, neutral, black, and earth green wires for safe and efficient operation. Safety devices. Safety devices protect electrical circuits from excessive current print. Electric fuse, earth wire miniature circuit breaker, MCB. In summary, we explored the magnetic effects of electric current, how current carrying conductors create magnetic fields, and the importance of safety devices in electrical circuits. Understanding these principles is crucial for both practical applications and safety in our daily lives. We hope that you have understood the topic. You can now study chapter notes, watch video lectures, and solve MCQ tests of this chapter on EduRev to ensure you score well in your school exams. And that's not all. You also get amazing courses for maths, science, English, Hindi, and much more for class 10. Thank you